Good afternoon, everyone. We are very excited to be here again. We are INTERALAGE, the network of Latin American students in space geophysics. Today, we are pleased to have a great talk by Dr. Cesar Bertucci. Dr. Cesar Bertucci received his Master of Science degree in astronomy from the National University of Córdoba and obtained his PhD in planetology and space physics from Paul Sabatier University in Toulouse. In 2004, he joined the Cassini missions magnetometers team at Imperial College London. Dr. Bertucci has worked with several space missions, including Mars Global Surveyor and Maven. And currently, he is a principal researcher at CONICET and a professor at the University of Buenos Aires. Today, Dr. Bertucci will talk to us about the solar wind interaction with Mars through the eyes of a LATAM research group. Thank you very much for being here with us today.
Thank you very much. Thank you, INTERALAGE, for the invitation. I'm very honored to be part of this conference series. So, well, in this talk, I would like to show you a few results that we have obtained in our group in Buenos Aires on the interaction between the solar wind and planet Mars, giving a particular perspective as a research group based in Latin America. In this talk, I would like to remember one of LAGE founders, Mario Akuna, who was a pioneer in space magnetometry. Mario designed and built magnetometers that flew on different space missions, such as Explorer, Pioneer 10, Pioneer 11, Voyager. Those two have left the solar system. And more recently, his sensors were on Mars Global Surveyor, the Messenger mission to Venus, and more recently on Maven. Unfortunately, he passed away in 2009, but his legacy lives on. Several young scientists from Latin America and other scientists from, excuse me, all over the world. And I think it's a good place to remember him. Here's a picture with the two of us at a meeting of the MGS, Mars Global Surveyor magnetometer team in San Francisco when I was doing my PhD in France. Most of the people in that picture are part now of the Maven mission. So it's a continuous study of planet Mars through the sensors created by a Latin American scientist. This is our group at UBA, at UVA. We look younger because it was taken several years ago, but we're still a small group. We work with a group of with three researchers and two PhD students at the moment. Laura Morales here on the left, Daniel Gomez. Laura is an expert on solar physics. Daniel is an expert in turbulence, MHD turbulence and simulations. And then our student Sofia Burne, who has recently graduated, and Gabriela Boscoboini, who's about to graduate early next year. And we have two MSci students in physics, Matias and Camila, who are currently doing her one-year project. We have other students who finished their PhDs a long time ago, a few years ago already. Norberto Romanelli, he's working at Goddard right now, and Nahuel Andres, he's back in Argentina working for the Department of Physics. So we're a small group, but very active, with a lot of international connections with different research groups all over the globe. So I'm going to talk about planetary magnetospheres. And to start with, I would like to talk about two different types of magnetospheres. So that would be like a zero order distinction between discrimination between magnetospheres. On the one hand, we have intrinsic magnetospheres. Those magnetospheres, the intrinsic magnetosphere are generated by the internal magnetic fields of magnetized planets. That is the case of the Earth, for example, whose magnetosphere is here on the left. The magnetic field of the Earth creates a pressure which can withstand the solar wind dynamic pressure, creating a pressure balance boundary called the magnetopause. As the solar wind is supersonic, it develops ahead of the interaction, we find a bow shock that decelerates and hits the solar wind plasma, so the plasma can flow around the magnetosphere. Inside the magnetopause, we find the magnetic field of the Earth, which is stretched down the tail, forming a magnetotail, where the field orientation is compatible with the direction of the dipolar moment of the intrinsic magnetic field. Between the magnetopause and the bow shock, we have the magnetosheath, which is a region of heated solar wind plasma and populated by waves and distribution function, which are heated with respect to those in the pristine solar wind. Planets like Venus, for example, have magnetic momentum 4 orders of magnitude smaller than the Earth's. And as a result of that, the solar wind and the magnetic field from the solar wind interacts directly with the atmosphere of these planets. This is the case of Venus, but this picture can be translated into Mars as well. And basically, it is the ionosphere and the upper layers of the ionosphere that host currents that whose function is to prevent the solar wind from penetrating the atmosphere. As a result of that, the magnetic field from the solar wind, also known as the interplanetary magnetic field, piles up in front of the ionosphere, and the solar wind is also decelerated. Of course, at the location of Venus, the solar wind is also supersonic, so a bow shock is formed ahead of this induced magnetosphere. And so a similar magnetosheath develops between the bow shock and a region where the magnetic field is highly piled up, and there is also magnetic field line draping, which is the effect by which the magnetic field lines go around the object, like drape around the object, and are stretched downstream, forming an induced magnetotail, where the direction of the field lines follows the direction of the upstream, or is compatible with the direction of the upstream interplanetary magnetic field, in such a way that if we rotate the IMF, the interplanetary magnetic field, around the direction of the flow, the whole induced magnetosphere will rotate with it. The outer boundary of the region with high pileup and very organized magnetic field line draping is the induced magnetospheric boundary, also known as the magnetic pileup boundary. So why are we interested in Mars as an unmagnetized object? Well, because Mars shows very clear signatures that on its surface that liquid water was flowing, carving channels known as outflow channels, as the one that you're seeing here in this picture taken by the laser altimeter on board Mars Global Surveyor. So the planetological question would be, well, all that water, where did it go? And so there are several explanations for the absence of liquid water on present Mars. One of them is that part of that water flew out into space. Part of that water that could have flown out into space was escaped due to thermal processes, but there is a fraction of that water that could have escaped via plasma processes. So we are interested in understanding how those plasma processes operate at present day on Mars, and how those processes can be measured, how their efficiency can be measured as we go back in time a few billion years ago, for example. So there are a few aspects of Mars that are very interesting. One is the radius. So Mars is a small planet with respect to the Earth. That means that the atmosphere of Mars would be more extended in planetary radii than that at Earth. That has to do with the size of the atmosphere. The axial tilt, which basically says that we have seasons on Mars, same as the Earth. And there is an interesting aspect here, which is the eccentricity of its orbit, which is one of the largest in the solar system. And that means that there will be a significant difference between the heliocentric distance at the moment of perihelion and the apohelion. So that will have strong consequences on the amount of radiation Mars gets from the sun. We're going to see that in a few minutes. Then the atmosphere is basically carbon dioxide, and in the upper atmosphere we detect oxygen and hydrogen, and also ions linked to water, such as O+, H+, but also O2+. So I'm talking about regions in the upper atmosphere above 200-kilometer altitudes. So this picture basically summarizes what we know so far about the Mars-solar wind interaction. This is a very nice cartoon that appeared in a recent paper led by Beatriz Sanchez-Cano. So basically we have the solar wind carrying the frozen-in interplanetary magnetic field. I'm not going to talk about that because I guess you probably know about this quite a lot. And then the presence of Mars can be perceived in the solar wind upstream from the bow shock in the form of ultra-low frequency waves at the frequency of at the protocyclotron frequency of local protocyclotron frequency. We're going to talk about that a little bit more in the next few slides. And then the flow goes through a bow shock, which is very small in size. So there are kinetic processes occurring at the bow shock. There is a very important concept, and is that the convective gyro radius of solar wind protons is more or less of the order of magnitude of the radius of the planet. So we expect the kinetic physics to be very important in this interaction. This is not the case of giant magnetospheres, for example. So so we have the bow shock, and then we have a magnetosheath with shocked solar wind plasma, and then we have a progressive contamination of the solar wind from by particles coming from the exosphere of Mars. Basically, what these particles do, these planetary particles do, is to remove momentum from the solar wind, as these particles are heavier than the protons that basically make up the solar wind. There's a little bit of fraction of alpha particles, but it's mostly protons. These particles coming from Mars are very slow and very massive in comparison. For example, O2+ or O+ ions, and then they systematically remove momentum from the solar wind. So the solar wind is not only decelerated by because of the presence of the ionosphere, which is a conducting obstacle, but also because of this mass loading process, which is very important at Mars. And so the frozen-in magnetic field piles up very quickly, very abruptly, defining the outer boundary of what we call the induced magnetosphere. The outer boundary of the induced magnetosphere is the magnetic pilot boundary, as I said earlier. Inside the induced magnetosphere, we have draped fields. Those fields have solar wind origin. But the curious situation is that also the MPB, the magnetic polar boundary, separates the magnetosheath, where solar wind ions outnumber planetary ions, from the induced magnetosphere proper, let's say, where planetary ions outnumber solar wind ions. So there is a change in the dominant ion population as you move from the magnetosheath into the across the MPB into the induced magnetosphere. So the question would be, what happens with the electrons? So it's a very interesting boundary. And then we have another distinctive feature of Mars, two more distinctive features. One is the crustal magnetic fields located mainly in the southern hemisphere of Mars that affect locally and partly globally the interaction, and the plume of heavy ions that escape along the direction of the solar wind convective electric field. So over the years, we have been focusing our studies on the processes that rule the transfer of energy and momentum between the solar wind and the atmosphere of Mars, because we think that that is the key to understand non-thermal escape processes. So in particular, we focus at processes at different spatial scales. For example, ULF plasma waves, as the ones that are observed upstream from the shock. Those waves have a length scales of the order of a proton gyro radius. Then we analyzed different electric fields at different scales. The convective electric field, that is a purely MHD scale field, so large scale. And then the ambipolar electric field and the Hall electric field that belong to or become more important at scales of the order of the ion inertial length, for example. So we analyze different plasma acceleration processes at different scales. And in particular, we are very interested in knowing how the mechanisms of transfer of energy and momentum change with seasons and over secular timescales and the variability with solar cycle. So we are also exploring different timescales. We are very limited because we only have one spacecraft, and as you probably know, it's not very easy to disentangle spatial effects from temporal effects. But with some assumptions, we are able to infer some important properties. So let me guide you through some of the results that we've obtained over the last decade or so. I'm going to talk first about the results from the Mars Global Surveyor mission I mentioned earlier. Mars Global Surveyor was in orbit around Mars between the end of the century and 2006. And it carried two instruments for plasma characterization: the magnetometers located at the ends of the solar panels of the spacecraft, and also the so-called electron reflectometer, which was basically an electron spectrometer for solar wind ions, for electrons, sorry. There was no ion instrument on MGS. And that was a very, very hard limitation for us. Nevertheless, the magnetometer allowed us to obtain a very good description of the magnetic topology around the red planet. And one of the most interesting results that we obtained was the fact that we could see how the exosphere changed along the planet's orbit around the sun by looking at the properties of ULF waves, ultra low frequency plasma waves. And to explain how they're generated, I will do it very, very simple with a simple cartoon. So we have Mars as a small planet that has a very extended exosphere. So as you probably know, up in the exosphere there are altitudes at which the different components of the exosphere evolve with height with different scale heights, because they do not collide anymore. The atmosphere is no longer mixed at high altitudes, and the lighter elements tend to be at higher altitudes than the heavier elements. So very far from the planet, and I would mean by that, I don't know, 10 planetary radii from Mars, we will find hydrogen, and that neutral hydrogen will get ionized by the extreme ultraviolet radiation, and that will create protons that are not protons from the solar wind. These protons come from the Martian exosphere. Now, when these protons are created because of the photoionization, they're almost at rest with respect to the planet in comparison with the solar wind, which at the location of Mars flows at a speed of 400 kilometers per second. So these exospheric protons face a solar wind moving at 400 kilometers per second, and then the addition of these two populations generate plasma instabilities that are studied in the frame of kinetic theory, basically solving the Blasov equation, which is Boltzmann equation for collisionless plasmas. And these plasma instabilities generate waves that are visible in the solar wind upstream from Mars using magnetometers. So this is an example of a typical observation of these waves with a frequency which is the local proton cyclotron frequency. This is a very specific property that arises when you have parallel propagation to the magnetic field because of the inversion of the Doppler shift. So, well, I'm not going to talk about that in detail. There are many papers that talk about that, like, for example, Brinca, 1991. All this theory was developed at the time of comets, observation of comets, starting with the comet Halley in 1986 and so on. So what we found, these waves were very easy to spot on MGS data. So what we did was to calculate an occurrence rate of these waves. That is, how much time, well, we consider how long MGS was upstream from the Martian bow shock, and then we computed what fraction of that time we saw waves like that. And what you can see in this plot that on the left is in the top panel is this occurrence rate as a function of time over half a Martian year. So you have at the bottom here, you have from 1997 to 1998, September through October 98. So if you take a look at this picture here with Mars seasons and heliocentric distance, is similar to observe Mars evolving from this position number 5, around number 5, up to 11, 12, more or less. So we went through perihelion from southern summer equinox. So that is the beginning of spring equinox, sorry. Then perihelion, southern summer solstice, and then southern autumn equinox. So you can see that the occurrence of waves peaks shows a peak at around perihelion. So what this was showing was that the occurrence of waves correlated very well with a property that was known to occur in the thermosphere. That was the expansion of the thermosphere due to the increasing flux of UV radiation from the sun as the planet got closer and closer to the sun. So we knew that this occurred in the case of dust storms. You know probably that these dust storms that sometimes become global dust storms, when the planet goes through perihelion, which occurs more or less at the same time as the solstice in the summer solstice in the southern hemisphere. So the combined action of the closeness to the sun and the increase in the radiation over the southern hemisphere triggers these sunstorms, dust storms, starting in the South Pole and sometimes progressing, covering the entire planet. So what we could find is that this effect is also seen at several planetary radii away from the planet in the upper exosphere by means of looking at the rate of occurrence of these waves. So we show that there is a link between the lower and the upper atmosphere of Mars. And then the Maven spacecraft came, and it was amazing because we could use several instruments to characterize the solar-wind interaction in Mars. Maven stands for Mars Atmosphere and Volatile Evolution Mission. It's the first mission dedicated to study the Martian atmospheric escape. It's been orbiting Mars since September 2014, and it has completed more than 20,000 orbits so far. It has lots of instruments. We worked in particular with solar wind instruments that look at the properties of the solar wind, the electrons of the solar wind, and also the ions of the solar wind. And we've also used data from the mass spectrometer that shows us the composition of the plasma, whether if it is solar wind origin or planetary origin. The Langmuir probe to measure the density of the plasma in collisional region, and then a magnetometer. And so we focused on two structures. Our students focused on the study, on the study of two structures. Sofia Burne studied the Martian bow shock, and the Martian bow shock has a profile in the magnetic field strength, as you can see, as the one you can see here at the bottom on the right. So the magnetic field strength as we cross the bow shock increases, describing a ramp and then an overshoot. So these structures are very typical of what we call a supercritical shock under quasi-perpendicular conditions. That is when the normal to the shock surface is perpendicular to the upstream interplanetary magnetic field. And for this particular orbit of Maven, Sophia and co-authors could be able to measure the size of these substructures. The foot, as you see in this cartoon here, the foot, that is the increase of the magnetic field prior to the ramp. The ramp where you see the steepest gradient in magnetic field strength, excuse me, and the overshoot. And a very interesting result was that the size of the ramp is of the order of an electron inertial length. And that is compatible with observations at Earth made by several spacecraft, by multi-spacecraft. I think it was the cluster mission. So we obtain very interesting results that places the Mars bow shock as describing similar features as other supercritical bow shocks. Those supercritical bow shocks are bow shocks formed by flows with particularly high speeds with respect to the local sound and magnetosonic and Alfvén speed. Also, with the size of the foot, Sophia could be able to measure the size, the speed of the shock, because the shock is not static; it moves around an average location. And for this case, she could be able to measure a velocity with respect to the planet of 20 kilometers per second. And the other topic I would like to talk to you about, and I will be finishing my talk with this topic, is the description of the Martian magnetosphere as a current system. And here I remember another ALAGE founder, Juan Roeder, who was a physics professor at UBA, at UVA, and then he moved to Alaska, Fairbanks. He worked in the Galileo project, and then he moved to University of Colorado. And he's one of our greatest minds in physics in Latin America. And he once, in one ALAGE conference, he mentioned that we should stop doing spaghetti physics. Spaghetti meaning talking about field lines, and talk more about what's going on with the currents, because actually what you can see and you can measure is or perceive is the current. So, well, it's not very easy to do that at Mars because we don't have multi-spacecraft missions. So it is very hard. You remember probably Ampere's law, and in order to get J, you need to compute the curl of J. And to do that in space, you need more than one spacecraft. And so far, we only have single spacecraft missions. So it's not very easy to infer a current system in the solar system apart from the Earth. So nevertheless, this study by Robin Ramstad and co-authors identified several current systems in the Martian environment. And what we did was to try to come up with a different way of measuring currents in a very simple way in order to know how the forces around Mars operate. For example, if you imagine the sun is on the left in this picture, there is a J cross B force responsible for the stopping of the solar wind ions at the MPB. This is linked to the gradient of magnetic pressure as the magnetic field piles up in front of the planet. But also there is a J cross B force responsible for the acceleration of planetary ions down the tail. And in this case, the J cross B force is associated with the magnetic tension and not the gradient of the magnetic pressure. So there are two different versions of that J cross B force, that Lorentz force, that could be studied. So we studied in particular this J cross B force here in this paper by Gabriele Bosco-Voynich and co-authors. And what I'm showing here is the magnetic field strength, the magnetic field components, the variability of the magnetic field, the fluctuations, the fluxes of electrons, and the density of solar wind protons as we move with Maven from the solar wind into the ionosphere. So we see the shock here, the bound shock here is this line that you see here. So the magnetic field increases as the flow decelerates. We see a lot of variability in the magnetic field, and then we see the entry into the MPB. As I told you, the MPB is characterized by an increase in the pileup of the field, so you can see how the magnetic field ramps up, and then it stays high in the induced magnetosphere. So the increase in magnetic field is showing that there is a current flowing there. How do you know that? Well, because of Ampere's law. You know that if you know the normal to the boundary, and you can obtain the tangential component of the magnetic field upstream from that boundary and downstream from that boundary, and you know that the jump in that component is due to the presence of a current surface current density. So we did under the assumption that the MPB was static because we only have one spacecraft, and under the assumption that the magnetic polar boundary is a planar discontinuity with a thickness h along the direction of the normal. So with this, we obtained an expression for the volume current density, JV. So with that, we could be able to obtain the J cross B force upstream and in the MPV in the subsolar location. So here are the results. So we get, I will summarize the results. We obtain currents of the order of hundreds of nanoampere per cubic meter. And that J-Crossb force that we obtain using this current is strong enough to stop the solar wind ions at the MPV. So it's pretty much compatible with what we are seeing, because in this picture you see how at the MPV the solar wind protons decrease in density. So it's probably showing that these particles are stopping there. So we have enough force to calculate the work of that force along the MPV, and that is comparable with the loss of kinetic energy. Basically, it's a very simple calculation. But the other interesting thing is that the thickness of the MPV is of the order of C over omega pi, and that is the solar wind proton inertial length in the magnetosheath. And what that means is that the thickness of the MPV is small enough for the ions to have room to be deflected, and it is the J-Crossb force that forces the electrons, on the other hand, to go in. So what we have here is like not a perfect boundary separating two different plasmas, but we have a Hall effect, which is a segregation of solar wind ions that would be stopped and solar wind electrons, or part of them, that would go through in order to ensure charge neutrality with inside the magnetosphere of Mars with the planetary ions. So this is a very interesting result that we would like to understand further. And we did some multifluid simulation. That's in another paper, more recent paper, where we could reproduce quite well the features measured by Maven. And I'm going to ask you to pay attention to this panel here. This is the simulation showing in the MPV. This is the MPV layer. The green region here is here. And this is the whole electric field, which is far stronger in the MPV than the ambipolar electric field and the convective electric field, meaning that that process is reproduced by simulation. That is very interesting because it is the multifluid character of the MPV which is manifesting itself through this current. So this is just a preliminary study. We think that we need to dig into these processes using more powerful simulations with better resolution and more realistic simulations, for example, by using hybrid simulation. So that's pretty much what I wanted to present today. As a conclusion, I would say that the study of the Mars-solar wind interaction contributes to elucidate the electromagnetic processes responsible for part of the atmospheric escape. There are groups that are focusing on that more specifically, but we are interested in analyzing the local mechanisms. Our group has provided relevant results, we think, regarding particle acceleration processes at different scales in the upstream region, bow shock and magnetic pala boundary. We will continue to do so. And future efforts will be aimed at incorporating machine learning algorithms. Well, you probably know that the Nobel Prizes have been given to the people who have thought about created machine learning. So we're following that trend to apply machine learning algorithms into the analysis of plasma boundaries to improve the detection of boundaries and in an automatic way, but also the criteria by looking at which are the most adequate quantities to look at in order to detect this boundary. This is crucial because with Maven, for example, we are facing the analysis of gigabytes and gigabytes of data that are very difficult to undertake with the amount of scientists that we have so far. So the help from these techniques will be very much appreciated. So thank you very much for your attention. And let me know if you have any comments or questions.
Thank you very much for the talk, Dr. Cesar Bertucci. Very interesting topic because I personally I like the investigation about Mars. We have a question in YouTube, but it is in Spanish. I translate or read in Spanish.
Yeah, if you want, you
What do you
can tell me
prefer?
in Spanish or tell it in English. I will answer in English and in Spanish.
Okay, so say, ¿los eclipses de las lunas de Marte tienen algún efecto? No.
If the eclipse of the moons have any effect, I would say no. But the moons, I will go on in Spanish later. But the moons play an interesting role by in plasma physics, in by providing particles via sputtering of the solar wind. So we are investigating that. So, así que yo diría no, en principio, pero sí se está investigando el rol de las lunas de Marte en la provisión de partículas provenientes del sputtering o de los golpes del solar wind sobre la superficie de las lunas.
Okay, thanks. In English and Spanish, the answer. So I don't know if we have other question. Well, oh, I have a question.
Yeah, sure.
Uh, with the with this instrumentation, how can we continue studying, for example, the ionosphere of Mars?
Well, the ionosphere of Mars has been thoroughly studied through what we call the deep dip campaigns, which are orbits at which the periapses have been lowered to 80-kilometer altitudes. So Maven could be able to even reach the neutral atmosphere. So through these deep dip campaigns, Maven could be able to provide relevant information about the structure of the ionosphere. And well, there are other instruments. For example, there is radar on board Mars Express that also samples the ionosphere. Beatriz Sánchez Cano from Leicester University is a specialist in the ionosphere of Mars, and she could be able to provide very relevant results on the ionosphere. So I would say the combination of several missions, Mars Express and Maven, and in the future the upcoming missions, for example, Escapade, will contribute to a better understanding of and a multi-point from a multi-point point of view. That's very important. It's not it's what you can get from several spacecraft operating at the same time is a lot compared to what you can get with just a single spacecraft, even if you have a very good plasma package or instrumental package. So now we're moving into solar maximum. So I expect that there will be a lot of interesting results coming from this unusual solar max. So I think this solar max has been the strongest solar activity in 20 years. So I guess we're gonna get a lot of interesting things concerning, flares and events like that have a direct impact on the ionosphere. So
Yeah.
be
So
ready
we have
for
many
that.
works.
Yes.
We have two questions
Yes.
in In the chat, Gabriela said, I knew the magnetosphere of Mars is not so stable like the Earth. How can this difference affect the models of the bow shocks?
The magnetosphere of Mars is well, I don't know what you how you would describe stable. I would say that in the sense that I guess what she means is that Mars is more reactive to upstream conditions than the Earth. For example, recently we've been co-authors of a paper on what happens with Mars magnetosphere when the solar wind disappears. That means when, for example, the density of the solar wind drops by an order of magnitude, what happens? Well, what we could observe was that the bow shock and the MPV expanded up to several couple of planetary radii. So in those circumstances, the models of the bow shock that we have are useless because the models that we have so far for the bow shock are very limited models that are close to be physical models, but the models we mostly use are static models. So those models are not useful when the solar wind is behaving in a very unusual way. So I think that is what she means. Those models are valid for a range of conditions, but of course, and I think the same happened with Saturn, for example, with Cassini. The model of the bow shock of Saturn is not very useful when you have the impact, for example, of an ICME. The system is so perturbed than what the parameters are far off what you normally get when you analyze, when you obtain an average, for example. So yeah, if the solar wind is highly perturbed, those models do not work very well. She laughs.
Well,
You're
in
welcome.
the Earth, the models fail sometimes.
Yeah. If you probably talk to an Earth and a terrestrial magnetosphere guy, he or she will say, no, it's not so stable. Well, it depends how you look at it.
Yeah. We have other question in YouTube.
Yeah, sure.
Um, say, Julie, um, is the rate at which Mars loses its atmosphere affected by the change in the solar magnetic field during the 11-year solar activity cycle?
So I guess the question is the escape rate is depending on the solar cycle?
Yes, yes.
Yes, it is. It is strongly dependent on the solar cycle. Also, why? Because of the occurrence of coronal mass ejections. As you know, as you probably know, over the declining phase, passing right after the maximum in solar activity, you tend to have more ICMEs and CIRs. So under those extreme solar wind events, you get more escape. Yes, that's right. So the escape is strongly affected by that. I remember, maybe I'm wrong, but I remember a factor of 2 at least in the escape rate, but I could be wrong or the situation could be even worse because we didn't have at the time of those papers, we didn't have such a detailed description of the solar wind. Now we have a special group within the Maven mission that provides space weather forecasts. So it anticipates how the solar wind is going to be in order to see what the impact is in the Martian atmosphere. So we're going to be able during this solar max to monitor more precisely in what degree the escape changes as a result of the response to more extreme solar wind conditions. So I think I also recommend to stay tuned for the upcoming papers in the next few months, because there are going to be a lot of papers on that, since we're going towards the solar max, or we're around solar max.
Okay, thanks. We don't have more question. Thank you very much, Dr. Bertucci, for the talk.
My pleasure.
And thank you for the streamer. And and see you for the next talk for the people of INTERALAGE. So bye bye. Thank you very much, and
Okay,
stop
bye.
the streaming.